The problem. You would have all seen these stats before. In US, buildings alone consume 40% of the energy ahead of industry and transportation. And if you look at just electricity, this number inflates to 72%. And if you focus on just the residential buildings, the heating, ventilation, and air conditioning combined consume 54% of the overall energy. So before moving any further, let me talk about an HBO series called Silicon Valley. In one of the episodes, there was this contest called TechCrunch Disrupt, and one of the groups presented an idea called a human heater, where they actually used microwaves to heat people up rather than heating the environment or the space in which humans are there. So fortunately or unfortunately, we have not reached this stage, and the HVAC systems that we have currently are here to stay at least for the near future. So HVAC systems are controlled by thermostats, which provide user comfort by maintaining a particular temperature called the set point temperature. And these thermostats vary in capabilities. For example, manual thermostats, as the name suggests, allow users to manually set a particular temperature. These thermostats are error prone because people might forget setting them to something called as a set back temperature before leaving. Plus, they may reduce user comfort as well because they cannot be activated before users can come home. So an improvement on that is a programmable thermostat, which essentially applies a repeating pattern, a repeating schedule. But as was pointed out in the previous slide, it is very difficult to come up with these schedules, especially in a multi-resident house, because everybody has a different schedule and schedules keep on changing over time. For example, kids might have some soccer practice in the summer months, so these things are pretty dynamic. So because of these factors, people end up using these thermostats as a manual thermostat itself. Next is a a smart thermostat. So smart thermostats use occupancy sensors and a learning algorithm to come up with a schedule without any user intervention. And they address the problems which were plaguing the programmable thermostat. And here are a couple of examples. Now, these smart thermostats cost around $250, which is more than 10 times the cost of an average programmable thermostat. And over the past few years, they have got pretty popular, but still the penetration is pretty low. So at least these figures are relevant for the year 2014, where in US, around 2% of the households have smart thermostats installed. These numbers are much lower for most countries in the world. So the natural question is, how can we make the remaining 98% of the dumb thermostats smarter? Now, to make dumb thermostats smart, we need sensors which detect occupancy, and there can be two approaches which can be employed. Approach one is to install a bunch of sensors en masse, and there has been quite a bit of work, including some work from this community, which has talked about it in detail. Unfortunately, these approaches cannot scale as they require user adoption. Another approach is, can we leverage a sensor which is already present in a house? For example, let's say an electric meters. Now, smart meters are devices which are networked and can measure electricity consumption at a fine-grained interval. Now, it is expected that by 2016, 75% of the households in US will have smart meters installed in their homes. And past work has shown that occupancy can be inferred from smart meter data. Chen et al. Used a mean power level based feature to derive occupancy from smart meter data, whereas Kliminger used past occupancy values to train their classifier. Unfortunately, in our case, we don't have past occupancy values, ground truth occupancy values to train our classifier. And we will talk about some of the issues which the mean power levels might have. So we formulate the problem as follows. So we would like to use existing smart meter data to make dumb thermostat smart. And to get to this, and to solve this problem, we need to answer the following questions. Like, can we infer occupancy from smart meter data? Can we derive repeating patterns in occupancy? And finally, can we derive a custom schedule? So here is the outline of my talk. Initially, I'll talk about the iProgram design, which answers questions which were presented in the previous slide. Then I will move on to the iProgram prototype that we have developed. After which I'll talk about the experiments which evaluate the performance of iProgram schedules. And finally, I will round off with conclusion. So let me initially talk about the iProgram approach. So we have smart meter data, which is passed through an occupancy detection algorithm. And we get these occupancy labels for the different time periods. We stack these different days one top of the other to get repeating patterns, which can be then passed to a schedule generation algorithm, which will give us a particular schedule. And if the programmable thermostat is Wi-Fi enabled, we can possibly even push this schedule inside the thermostat. So let us initially talk about the occupancy detection algorithm. And here we have used burstiness in smart meter data as a feature. So the key intuition here is that large power levels do not always correspond to occupancy. So in front of you, you have an example of a misaligned AC, and the true occupancy values are shown on top of the figure. So algorithm which is based on the absolute power level might be put off by this kind of misalignment, and the inferred occupancy can be faulty. So burstiness, rather than looking at the absolute power level, it looks at the change in the power levels. And a burst essentially corresponds to multiple time periods which has greater than average change. So this essentially indicates a proof that someone was occupied in a house. But before using burstiness, we would like to filter out some of the large repetitive loads. We have seen in a previous talk that there are these loads which run in the background, for example, air conditioner systems and refrigerators. And we used time series decomposition to remove these background loads. So once we have these occupancy labels for the different time periods, we would like to derive the probability of occupancy. And probability can be calculated for the different time periods in a given day from 0 to 24 hours. And we select the days for calculating the probability based on the schedule that we want. So in front of you we show a 7-day schedule where we generate a different schedule for each day of the week. So we get probability of occupancy something like this. Whereas if we want a 5-2 schedule, that's a week and weekday schedule, then we will just have 2 set of days, one for weekdays and another one for weekends. So once we get this probability of occupancy, it's obvious that to get a schedule, we have to look at the low occupancy periods and set the thermostat to a set back temperature. But we have a couple of objectives in our optimization problem. First is we want to optimize on the user comfort, and the second is energy savings. And these two objectives are orthogonal in a way. So we are introducing a couple of variables here. So the miss time is a time period when user is at home but the thermostat is off, which essentially corresponds to user comfort. And waste time is a time period when user is not at home but the thermostat is on, which corresponds to energy savings. In an ideal world, we would like to minimize both these variables. So we employed a greedy algorithm to generate schedules, and essentially this algorithm will take a budget of miss time as a parameter to decide the schedules. And finally, we end up with a schedule which looks something like this for the 7 days of the week. So now we move on to the iProgram implementation. So we built a prototype as a web service where users can log in and input their smart meter data in the form of CSV files. And we expose a couple of APIs. One of them is to upload the smart meter data, and the second is to download the schedule that we generate using our algorithms. And we generate 2 kinds of schedules. One is an all-day schedule, which corresponds to a 7-day schedule, different schedules for each day of the week, and a weekend weekday schedule. And here are a couple of screenshots, one of them showing the occupancy labels and another one showing the actual thermostat schedule. Next, I'll move on to the evaluation. So we evaluated iProgram schedules on a geographically diverse data sets. So first one is the Yuma star data set, which has 2 homes based out of northeastern United States. And the eco data set home has 5 homes in them spread across 2 seasons. It's from EU. And the Pecan Street data set, we have selected around 100 homes, with primarily these homes are from the southern and the western United States. We conducted 2 sets of experiments. First is a qualitative validation of iProgram schedules, which essentially evaluates, which is evaluating iProgram schedules for the data sets which I just described, using the different performance metrics. And the second kind of experiment is a real-world user study, where rather than evaluating using some performance metric, we have generated schedules and we have shown users to give a rating to us. So before moving any further, let's talk about the performance metrics. For occupancy detection part, the accuracy is pretty straightforward, which is the fraction of correctly labeled time periods. But in our domain, where we have 2 labels, one is occupancy and second is there is no occupancy. In these binary classification problems, accuracy is a poor measure. In a sense, if a user is at home 90% of the time, then a naive occupancy detection algorithm can say that the user is always at home and the accuracy is 90%. Well, this kind of an output is not really useful. So Matthews correlation coefficient is resilient to imbalanced data sets, and it's a pretty good measure for a binary classification problem like occupancy detection. And the performance metric for schedule generation are miss time and waste time, which I just discussed. That is, miss time is the time period when user is at home but the thermostat is off, and waste time is the time period when user is not at home but the thermostat is on. And mismatch time is essentially a linear combination of miss time and waste time. We initially discussed the error in the occupancy detection part. The graph in front of your screen, the data that we used is the eco data set and the Yuma star data set. On the x-axis, we have the home IDs, and on the y-axis, we have percentage of time. And we have these stacked bar graphs where the different colors correspond to the true positive, true negative, false positive, and false negative values. If you combine the bottom 2 bars, bottom 2 colors, that is green and red, you will get the accuracy. And on top of each stacked bar graph, you see a numerical number, which is essentially the MCC values for those individual homes. So we find that the accuracy that we get is around 75 to 95%, and the MCC values are in the range of 0.28 to 0.76 with a mean score of 0.53. These are in line with the work done by Clemenger et al., but we do not use past occupancy values to train our models, so we do not have access to that. Moving on to the error in schedule generation part. So here the data set that we used is the Pecan Street data set, and the schedule generation algorithm, the parameter that we have given is a miss time of 60 minutes. So here again on the x-axis we have home ID, and on the y-axis we have the mismatch time. And the red colored dotted line essentially indicates a mismatch time of 60 minutes. Now we notice that around 30 homes out of this 100 have a mismatch time of about 60. This is because these homes do not have a repeating occupancy pattern, and talking about a repeating schedule for these homes doesn't make a lot of sense. So in the next set of experiment, we only consider the first 70 homes. So we also wanted to evaluate our algorithm to see if it works on inefficient homes where the HVAC systems might be misaligned. So we synthetically shifted the HVAC loads by values between -2 to +2 hours with a gap of half an hour. So we conducted different experiments, and the results are in front of your screen. So we find that even with this perturbation, the mismatch times are not changing for most of the homes. So clearly, iProgram is insensitive to misalignment for most homes that you can see in front of your screen. Next set of experiments we would like to talk about is the energy savings. So here we had 4 set of experiments with different missed time budgets ranging from 15 minutes to 60 minutes. And for comparison, we had 3 different kinds of schedules. One is a 1-day schedule where we consider all days as same. Second is a 5-2 schedule where we have 2 sets of days, weekends and weekdays. And the third is a 7-day schedule where each day of the week we have a different schedule. On the x-axis, you again have home ID, and on the y-axis, you have the average per day savings in kilowatt hours. So one of the first observations is that the 7-day schedule is better in terms of energy savings than a 5-2 schedule, and which is in turn better than the 1-day schedule. And the average energy savings is in the range of 1 to 5%. Now, this number may seem rather small, but when applied on a large scale, this may result in significant energy savings. Another thing that we observed is that most of the homes in the Pecan Street data set have smart thermostats installed in those homes. So the headroom that we have in terms of energy savings is pretty limited. And also these homes are not necessarily representative of United States, where only 2% of the homes have smart thermostats installed in them. So we believe that the savings for an average home might be much higher. So now we'll move on to the user study. So for this, we collaborated with a local utility, and we asked users to provide consent for us to use their smart meter data. And only 8 people came forward, so it's a very small number. So after the consent, we had access to 3 months of smart meter data at 5-minute interval. And we essentially prepared a questionnaire which included many questions, such as the type of heat source that they use. Is it heating oil, gas, or electric? The type of thermostat, is it manual, programmable, or smart? And also how users interact with thermostats. Do they manually set it, or do they program it? And also, based on the data that we received, we prepared a 7-day schedule. And we asked users to provide a rating from 1 to 5, 1 being poor and 5 being excellent. So the results are in the form of a heat map out here. Red and white colored grids are good. And some of the findings are the 73% of the schedules, we got a rating of 3 or above. Especially one home, that is the 4th home, we found that that household gave a very poor rating, and we found that this home belonged to a retired couple which had very high occupancy rates. So we went wrong there. And also 3 out of the 8 homes gave us a rating of more than 4 on an average. In conclusion, we have shown that iProgram infers schedules from smart meter data. We developed iProgram prototype and also give access to some of the APIs. We also evaluated iProgram schedules on different data sets. We also conducted a user study to validate our method. And as part of our future work, we would like to conduct a wider user study in collaboration with the same utility that I talked about. So that's it from my side. Thank you.